Hello, hello, Marvelous Algebra 1 students, and welcome back to Topic 9, Factorable Quadratics. This is our second to last lesson in this unit, and we really need to address the other half of Goal 25 that we've discussed before. Goal 25 is saying that we should be able to graph a factorable quadratic equation in the form y equals a times x minus p times x minus q, and we've done that before. That is intercept form. But there's an or here, and the or says y equals ax squared plus bx plus c. Well, it should say bx. Now, today's daily learning target is to actually graph an equation in y equals ax squared plus bx plus c. And we know this is standard form. We've seen it written out before. No parentheses, biggest exponent first, next biggest, and so on and so forth. And so we should probably get to that. So we're going to start with this standard form equation and do a few things that we've already done with it before. A and B ask us to just evaluate the equation with two different inputs, and C asks us to find the zeros. So go ahead, warm up that brain, try A through C, and then you can quickly check and see how you did once you unpause. Ready, set, go. All right, hopefully you did okay here. Remember, when we're just doing f of something, that means that we are taking the x and replacing the x with whatever our input is. So I'm going to replace the x that the squared is attached to and replace the x that the negative 2 is multiplying by. And what are we replacing it with? Well, we're replacing it with 0. Okay, so this will tell us that f of 0 equals, well, 0 squared is 0. Negative 2 times 0 is 0, and minus 8. So I think that tells us then that f of 0 equals negative 8. When you input 0, the output is negative 8. And you should remember, and this will become important later on today, that although you can write your input and output using function notation, the other way we have to show an input and output is, of course, a coordinate pair. Our input was 0, the output was negative 8. All right, let's do the same thing again. F of negative 1 this time. And by the way, you should know that you can, of course, use your calculator to simplify a side of an equation. Right? There's nothing to simplify on the left side. It's just f of negative 1. But your calculator can do all of this at once. And if you want to check your work after, you should probably use the calculator. Just don't forget your parentheses. They're super important, especially when dealing with a negative. So negative 1 squared means negative 1 times itself. That's positive 1. Negative 2 times negative 1 is positive 2. And then there's the minus 8 at the end. Then we just work from left to right. So 3 minus 8. And it looks like f of negative 1 is negative 5. Or as a coordinate pair, negative 1 is the input, negative 5 is the output. Finishing this off, they do ask us to find the zeros, and hopefully we remember how to do this. To find the zeros of an equation, we set the output, the y, to 0, and we find the x. So if we're looking at this equation, do you see a y anywhere? Well, you don't, but hopefully we remember that f of x means the output. That means y. So we're going to set that to 0 and keep all the x's in here. We're trying to find the x's that make the equation 0. And then we look at this and go, well, wait, how do we solve this again? Because we've really learned two methods to solve equations here. We've discussed in the past that if there's more than one x, and in this case there are two different x's that we won't be able to combine, we don't want to use SADMAP. SADMAP is used to isolate a single instance of x. There are multiple x's, no SADMAP. So what's the other way to do it? Well, the other way we've worked on is that box method, factoring, right? So we're going to go through and just factor this. Now, this is one of those cases where you don't need the box, but you can use the box if it helps you, right? You can put the 1 in front, and you can certainly go through and make the box and do everything here. But I mentioned this before in our factoring unit. The majority of problems you're going to be asked to put in factored form, not all, but the majority, will have a 1 in front. And so we need to get comfortable at just quickly factoring without the box, especially when you get to a test. If you have to draw the box every time, you're going to be pretty sad in terms of time. So what do we need to do? Well, we know it starts with x and x because that's the only way that we're going to make x squared. All right. Then we need to make negative 8. So these two at the end that don't have x's will multiply to make that negative 8. The only way to make 8 is either 8 and 1 or 4 and 2. I don't think 8 and 1 can combine to make 2, but I think 4 and 2 can. So I think we need a 4 and 2 here. Those multiply to make 8, but to get negative 8, one of them has to be negative. Which one? Well, that's got to be a negative 4. Negative 4 plus 2 is negative 2. Negative 4 times 2 is negative 8. Now we're in factored form, and the reason that we did this is because we want to use the zero product property, which says if you have factors attached by multiplication that are equal to 0, we can make two smaller or as many smaller equations as we need. And now these should be pretty easy to solve, right? We add 4 to each side. And again, if you can do this step in your head, I would definitely suggest doing it. You certainly don't need to show the plus 4. At this point in your algebra career, you should be pretty comfortable solving one-step equations in your head. And x equals negative 2. All right. Reminder, you could write these as coordinate pairs as well. Coordinate pair-wise, we have an x of 4 will cause the y to be 0. And we also have an x of negative 2, which causes the y to be 0. All right, so there's our brief reminders. The rest of today I think should go pretty quickly because we actually already know how to do everything involved with today. It's just some extra practice. So let's do a little bit of a recap. We know three forms of quadratic equations. Topic 7 introduced us to the idea of quadratics in vertex form. So we'll either call this vertex form or sometimes we call it HK for hopefully obvious reasons. Vertex form is really easy to graph the vertex, but it's definitely more complicated to find the zeros, to find the x-intercepts. You have to do SADMAP because there's only one x here, and it takes a little bit of time. You have to do a square root, plus minus, bunch of math. The second type of equation that we've practiced the last couple classes is this intercept form. And I mentioned sometimes it's called factored form as well, which should be pretty obvious because it's in factored form. And it's intercept form because it's very, very easy to find the x-intercepts, right? You take your factors, set them equal to 0, just like we did up here, and the x-intercepts are pretty darn straightforward. This last one we've mentioned already once today is called standard form. And standard form we've also done in the past. We were introduced to that in topic 8. Biggest exponent first, it's a degree of 2. And as we go through, we spent time on vertex form, time on intercept form, but the one that we haven't actually graphed yet is standard form. But luckily, since we know how to graph intercept form, we actually already know how to graph standard form. So let's try one. In fact, let's try the opener. So here's our equation, standard form. Let's state the y-intercept. Well, the y-intercept here is found by replacing x with 0, right? So I think we have to find f of 0. And to do that, it'd be 0 squared minus 2 times 0 minus 8. But I think we actually did that on the opener up here, isn't it? Negative 8. So I'm just going to say it's negative 8. Now, a couple of things to note about the y-intercept. First, I'm going to plot the y-intercept on the y-axis. But second, this standard form is actually the quadratic idea of mx plus b, right? So if we have this standard form up here, and then we have y equals mx plus b over here, this made a line. We were introduced to this in 6th and 7th and 8th grade, and then at the first semester as well. And when we said mx plus b, we said that m was our slope, and that's not really relevant for our quadratics here. But then we said the b at the end stood for the beginning of the graph, but realistically this b is the y-intercept. And notice that this c value at the end, even though there's two b's here, it gets a little confusing, this c value at the end is also going to be the y-intercept. Can you see why? It's because when you replace the x's with 0, they all cancel, and so we're just left with any number not attached to x. And so this is kind of like our slope-intercept form, except they don't give us the slope, they just give us the y-intercept. All right, we need to state the x-intercepts, and just a reminder, I'm going to say C opener, because I don't have enough room to put the work here. Finding the x-intercepts does have a little bit of work. Not a ton, but you do need to really be able to go from here to here efficiently. And if you're not sure how to do it without the box, you'll have to draw a box each time. And so it's a little time consuming, maybe an extra minute, but it's not terrible. And then, of course, you need to solve your little mini equations here. But this is all the work for the zeros, which again are a fancy way to say the y. Nope. To say the x-intercepts. There we know. So we have two x-intercepts here, 4. So we have 4, 0, and negative 2, 0. Let's put those on the graph. 4, 0, and negative 2, 0. All right. I think then we still have a little bit more work to do because, and this is what a lot of students do. Don't do this. I'm going to erase it. A lot of students go, oh, okay, we've got this, and then we've got this guy over here. That's not right because that would mean that the axis of symmetry goes right through the middle. And is this x-intercept the same distance from the axis of symmetry as that one? No, it's not. We know that symmetry means those points should be the same distance from the center. And in fact, the mistake you made, do you see it, is that this point is not the vertex. The vertex has to occur between the two x-intercepts. Now, we've discussed before that to find the vertex, you could add these 2 points together and divide by 2. That'll find any number in the middle. That's our mean. But I think counting is probably more efficient here, right? If you go in 1 in each direction, and then a second, and then a third, I think we can probably see that 1 is directly in the middle. Now, as soon as you know that 1 is directly in the middle, I like to go through and just do the axis of symmetry. That's where that's going to be, right? So our vertex is going to be the point 1 comma something. Now, the problem is I don't know how far down the vertex is. I know it's probably going to be further than -8. It couldn't be up here. That would be a weird parabola, and clearly that wouldn't be the vertex. So it's got to move down somewhere down here. All right, so let's go ahead and find the y-coordinate of the vertex then. To do that, I think we just need to input 1 into our equation. So we're just going to find f of 1, and that's going to be 1 squared minus 2 times 1 minus 8. It becomes 1 minus 2 minus 8, and you can, again, do all this on your calculator if you'd like. Let's see, 1 minus 2 is -1, and -1, oops, I'm jumping ahead, minus 8 gets us -9. So there we go. All right, our vertex then is 1, -9 right here. And we usually like to include 5 points with this parabola, and I think we can because of that symmetry, right? The y-intercept is 1 space away from that symmetry, so I can put its symmetric point on the other side. And we can finish off our parabola. Something like that. Looks pretty darn good. Okay, so really again, you know how to do all of this. So even though we hadn't particularly graphed standard form before, you know how to find the y-intercept every time. Replace x with 0. You know how to find the x-intercepts. You set y to 0 and solve. That's your box method there, factoring. And then we know how to find the vertex for these because the vertex is always in between, exactly in the middle of the two x-intercepts. Okay, so let's go ahead and discuss one more important concept for the day, and then you guys are going to do some fun trade-up cards to get interacting with each other, and that should be it for the day. So the last idea that we need to cover for today is the idea of a maximum or a minimum of a parabola. So we're going to go ahead and draw 2 sample parabolas below, one with a negative a value and one with a positive a value. And remember that a value, just demoing back on the front here, that a value is the number that's out front. It affects how steep or how shallow the parabola gets. It's not the slope, but it controls how the steepness, it controls the slope of the parabola at every point. And we should know, like on this first one, if a is negative, right, a is less than 0, this means that a is negative, that our parabola is going to open down. It's going to look like this anytime you have a negative a value. However, if you have a positive a value, our parabola is going to open up, right? You can think slope. If the slope is positive, it goes up. Negative, it goes down. Kind of looks like a smiley face too, or a frowny face. Okay, now the location where a maximum or minimum value occurs is the x value of an equation. For example, on the previous page, the minimum value is located where? Well, on the previous page, we have a parabola. Okay, and where's the smallest or the most minimum value on this parabola located? Well, clearly it's this point because that is the lowest point on the parabola. Where does it occur? Well, the location of the minimum occurs at x equals 1, right? And so we can even label our 2 graphs up above. This point up here is going to be the maximum value of the parabola. It's the biggest it ever gets. And this guy over here is going to be, of course, a minimum. Now, can a parabola have a maximum and a minimum? Here's the biggest point. Shouldn't there be a smallest? Well, remind me what these arrows mean. These parabolas go down, down, down forever, right? They continually go down, and so there's never actually a smallest point, a minimum, if you will. Sometimes students say, well, isn't the minimum negative infinity? And you're kind of right. But infinity isn't actually a number. Infinity just means really, really far, right? And so in this case, negative infinity can't be equal to the minimum. Negative infinity just means there is no minimum. It goes infinitely negative. So we don't actually say that there's a minimum. Same thing, there's no maximum here. The parabola goes up infinitely far. It doesn't reach infinity. It just keeps going forever, so there is no maximum. All right, now we discussed that the location is the x value, but the actual value of the minimum and maximum is the y value. So if we look up here, the minimum of this parabola is located at x equals 1, and the actual value is y equals -9. So that tells us you input 1, and that will find the minimum. The actual value of the minimum is -9. All right, so let's try and put that into practice with a quick word problem, and then we'll get our couple trade-up cards, and we should be good to go. All right. Example, Ruby throws a stone off the bridge into the water below. Okay, good so far. The stone's height in meters above the water after some time in seconds is given by that equation there. Now, just a reminder, right? Reminder-wise, the path of the stone is actually going straight down, and you can enjoy my drawing skills here, right? We've got our water right here, and then we've got this, I don't know, adorable bridge that's hanging out over here going across the water, and then Ruby is standing up here, very excited, yay, and she's throwing a stone, we'll do the stone in purple, into the water. Really, you should think of just dropping it straight into the water, okay? So the stone is going straight down. However, if you think about how the stone moves, right when she drops it, the stone's moving very, very slowly. Then, as the stone gets closer and closer to the water, it picks up speed. So even though she drops it in a linear direction, our graph is going to be a parabola. And in fact, notice the -5 here. Our graph is going to be a downward-facing parabola. Okay? This downward-facing parabola at the top, where it's flat, is basically the spot where the stone starts from, and it goes down, 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 down from there. Okay, now let's go ahead and start with A. Evaluate h of 2 and interpret your answer. You might want to use a calculator for this. It's up to you, but we know now that h of 2 just means replace all the inputs. In this case, t is the input with 2's. If you don't want to use a calculator, that is awesome. Okay, you just need to make sure you can check your work. I'll try to do some mental math, and hopefully I won't screw it up too badly. This is 4 times -5 is -20. Okay, this is +20 right here. That's nice. And then the plus 15 at the end, I think those will cancel, and it just leaves us with 15. Okay, so after, or maybe I should say at 2. What is this 2 again that's right here? Well, 2 is the t, and t stands for time. Okay, so at 2 seconds, almost wrote at 2 time. At 2 seconds, the stone is 15, what? 15 meters? 15 meters above the water. Not too bad, right? All right, B. How many seconds after being thrown off the bridge will the stone hit the water? Well, again, if we look at our pretty picture over here, we're dropping this down to the water. We're assuming the water is at a height of 0. And so I think if you picture like an XY axis going on over here, something like this, then the stone's going to hit the water at the x-intercept, right? That's when the height, here's your height axis, right? The stone starts up here, but that's going to be when the height is 0. Okay, so if we want to figure out when the stone hits the water, let's figure out when the height, when the output is 0. So we'll need to solve 0 equals -5t squared plus 10t plus 15. This is also finding the zeros of the equation, or the x-intercepts, isn't it? Okay, so if we do that, I'm noticing that there's a -5 common to all of them. You could take out a +5. The reason I'm going to take the -5, though, is because that's going to leave me with that 1 in front of t squared again, and I think that's going to help us out. So negative 5, and then we're going to get to t squared. This is going to be a 2t when you divide by 5, right? 10 divided by 5, and 15 divided by 5 is 3. But careful of your signs. Negative 5 times t squared gets the right sign here. Negative 5 times 2 will give us a negative 10, so I think this needs to be a negative. If you divide or multiply by a negative, it changes all of the signs to their opposites in the equation. Okay, so minus 2t minus 3. All right, the nice part again is I can go ahead and probably factor this equation pretty quickly. This is going to be t and t. Okay, and then we're going to need to figure out what multiplies to make negative 3 and what adds to make negative 2. There's not many things that multiply to make negative 3. I just think it's negative 3, or let's just do 3 and 1. And then to add up to negative 2, I think the 3 needs the negative sign. Ta-da! And then actually solving this isn't bad at all, right? To solve, t plus 1 equals 0, or t minus 3 equals 0. And then we just subtract the 1 to get negative 1, or add the 3 to get 3. Very nice. Part C asks us to find the maximum height of the stone, and at what time does it occur? Well, I think maybe at this point we should actually start to graph this situation to see what's going on. So we have a few key points. We know that at a time of negative 1 and at a time of 3 we have x-intercepts, we have zeros. And we actually also know one other thing too. We also know that at an input of 2 we have an output of 15, so 2 comma 15 will be somewhere up here, right? So we can at least get a general idea of what's happening. Now again, this is not our parabola. We know that this point here is not the vertex. And we know it's not the vertex because it's not exactly in between our two x-intercepts. So if we're looking for the maximum height of the stone and I draw some sort of parabola like this, our vertex is going to give us the maximum height. And it's also going to tell us the time when the maximum height occurs. So this part C is just a fancy way to say, find the vertex. So let's do it. The first part of the vertex is going to be the x value. And I'll put that line of symmetry up there too. Okay, so if we look, I think hopefully we can see that exactly in between negative 1 and 3 is positive 1, but I'm not going to put a point there. I am going to put the axis of symmetry. Okay, so axis of symmetry wise, that tells us that our vertex is going to be 1 comma something. We just don't know how high up that vertex line we get. Luckily though, we know how to find this. At a time of 1, that's our input, we just need to use our equation, h of t, and we need to find h of 1. So negative 5 times 1 squared plus 10 times 1 plus 15. And as we do the math, we'll get negative 5 plus 10 plus 15. This to me looks like 25 minus 5, which I think is 20. So 1 comma 20. And you'll actually notice on here that our graph just goes up to 20. We usually try to design them to fit the parabolas pretty perfectly. And so I think that's looking pretty darn good. Okay, so we actually now know what the answer is to this question. What's the maximum height of the stone? So the max height is 20 meters. Okay, and this is at a time of when? Of 1, right? Of 1 second. So I think I have to revise my Ruby stone throwing off of a bridge thing because it seems like that Ruby's stone actually gets higher than where she is. So it seems to me that what's probably happening is she threw the stone, and I should probably revise my drawing a bit here too. It seems like she actually is going to throw the stone up in the air first. So it's going to go up, and then it's going to go straight back down here. So I think that would make our parabola make a little bit more sense. So I think that looks pretty nice. Yeah, then last but not least, they say degraph the situation. Well, we're pretty much done with the graph, I think, aren't we? The only thing we have left to do is maybe draw the parabola. We could maybe get one more point if we wanted, right? Our last point on here. If we looking for those 5 points, here's the symmetric point. This looks like it's 1 away, so I think we could also go 1 away over here. That actually looks like the y-intercept, doesn't it? And I think that would even be confirmed by looking at the c value here. That is the y-intercept. Okay, so let's go through and sketch in that parabola up here and then goes way back down. Awesome. Okay, well, at this point, you will need a partner, and you're going to be doing a series of trade-up cards. You're going to be alternating which partner brings up the trade-up card to your teacher. So each of you are going to have a card, and it's going to be the same card, and you're going to work together. But once you're done, you're going to take your card and your partner's, and you're going to bring it up to your teacher. Your teacher's going to quickly check that card to make sure it's good, and then they're going to trade you up. They're going to hand you the next card. There's a series of 4 trade-up cards here, and your goal is to be really the first one done, but definitely get it done by the end of class. Your teacher will definitely be quizzing you when you bring up the card and say, oh, wait, how did you get this number? Where did this come from? And so that means you need to make sure that both you and your partner can explain that math. All right, at this point, go ahead and start that first trade-up card. If you do need any help, you can always unpause and listen, but let's see what you guys can do. Ready, set, go. All right, well, our first trade-up card asks us to graph the equation y equals x squared plus 2x minus 3. Include the math that you used to find the y-intercept, the zeros, and the vertex. Lastly, state the domain and range. You'll have to draw your own coordinate plane, your own xy axis on here. Well, I'm actually going to do the math first. I think that's going to make more sense, and then we can figure out how big we need to make the coordinate plane from there. So let's go ahead and start with a few key pieces. We'll start with that y-intercept. Okay, and so to find the y-intercept, you just substitute 0 in for our x's. We've done this before. Or, and you can see it right now, you could have just looked at the c value and said that the y-intercept is -3. I always like to write it as a point, though. We input 0, we got an output of -3. Okay. Next up, we want to find the zeros, which is a fancy way to say the x-intercepts. And to do that, we replace the y with 0. So 0 equals x squared plus 2x minus 3. Okay, so to find these zeros, I think we're going to go through and probably need to factor this. That's your box again. You can totally show that box method. Don't forget it because you will need it sometimes. However, I think in this case, because there's that 1 in front, we probably don't. We know it starts with x and x. We need to multiply to make 3, and the only way to do that is 1 and 3. And then we need to add up to get a positive 2, so I think the bigger number is going to get the sign that it adds up to be, like so. 3 minus 1 is 2, 3 times -1 is -3. Ha! We're looking great. Once we're here, zero product property, x minus 1 equals 0, or x plus 3 equals 0, and we find that we have 2 zeros, or 2 x-intercepts, -3 and +1. All right, last but not least, we need the vertex. Vertex-wise, since I haven't graphed anything yet, we might want to remember how to find the number that's exactly in between two numbers, and many of you can probably count that in your head. I'm just going to quickly remind you, though, that you can always add those two numbers together and divide by 2. So that'll be -3 plus 1 is -2, and that gets me -1. Again, can we see that -1 is in between 1 and -3? Hopefully. Well, then we know that our vertex, and I'll just put this down here, will be at the point -1 comma something. Comma what? Well, that's why we have an equation to change x's into y's. We know the x is -1, so it becomes -1 squared plus 2 times -1 minus 3. Okay, that's going to give me 1 minus 2 minus 3. This is 1 minus 5, and 1 minus 5, I think, is -4. All right. Well, we have pretty much all the information we need, so let's go ahead and sketch in this xy axis. When we do that, we definitely know we need some negative numbers on the y-axis. We see all those, right? We will need a few negatives on the x and a positive as well. It doesn't look like we need much on the positive side of the y-axis, but because our parabola goes up, we might want to include some. So I'm thinking my graph will probably be okay if I do something like this. All right, let's get our x's in. 1, 2, 3. 1, 2, 3. We definitely need to go out to -3 because that's one of our zeros, right? And here's 1, 2, 3. Good. Then we'll just put something here. Our y's only need to go down to -4. So 1, 2, 3, 4. And I think we can probably start plotting our points. So the y-intercept, 0, -3. Very nice. The x-intercepts, 1 and -3. And the vertex, -1, -4. and reminding you that's our axis of symmetry. Okay, with symmetry, we know this is 1 away, so we can do 1 on the other side, and we can sketch in this beautiful parabola, like so. Looks pretty good. Last but not least, we do need that domain and range. Our domain hopefully is second nature now. Our domain measures what we're allowed to substitute into the equation. We can put any number in for x we want. You could also think of it as the width of our graph, and parabolas do get infinitely wide, so we say the domain is all real numbers. Range measures the answers you can get here, and it's easiest to see on the graph. All of our answers, all of our outputs, or the height of the graph is restricted because there is a minimum value here. The lowest we get on here is -4, and then you can see the graph goes up from there. So we say the range is y is greater than or equal to -4. It can be equal. There's a solid circle there. The other way that you can say that is you can say we go from -4, we include -4 with the bracket, and we go up infinitely far. You can't include infinity, it's not a number, so we just leave it with a parenthesis. All right, hopefully you had all that information and you've traded up your card, so why don't you try trade up card number 2, right? Ask you to do the exact same thing, so ready, set, go. All right, I'm going to try to do the same thing as well. We'll start with the y-intercept, and we'll take that nice shortcut. I can see that the y-intercept is going to be 0, 5. X-intercepts. This one we might need a little bit more room for, because when we set y to 0, I might notice that there is a number in front of x squared that is not 1. And, unfortunately, you also might notice that there is nothing common to all three. So let's hit that box method. Okay, box-wise, let's see, try to save enough space over here. We know this will be -4x squared, and we also know that this will be +5. Okay, we are looking for two numbers that will split up my 8x, and they multiply to equal the first times the last, so that becomes -20x squared. All right, well, let's test those multiplication facts. To get to 20, it's 1 and 20. 2 and 10. Oh, I bet it's 2 and 10. So let's check this out. Right, we're going to go ahead and get 10x and 2x, 10x and 2x. And can we see if we do 10 minus 2, it makes 8. 10 times -2 is -20. Like so. Looks pretty good. Then we have to find the outsides. When we find the outsides, it looks like 4 and 2 both have a 2 in common and an x. Okay, and then this one's a little bit trickier because we have to think, actually, I'm going to take the negative as well. The negatives line up, so let's do that too. You might not have noticed it, and I didn't right away either. And if you didn't have the negative here, this would have to be -2x, which is fine. There's nothing wrong with that. You'll still get the same answer. It'll just look slightly different. But I was like, oh, we need a negative. They line up. Might as well go there. Okay, this will be a +2x then. -2 times 2x times x. 2x times 5. -2 times 1. And we can go through and finish solving, I think, right? So we have 0 still equal to, but no longer the standard form. We've converted it to factored form. So 2x plus 1 times -2x plus 5. And we have two equations to solve here. 2x plus 1 equals 0, or -2x plus 5 equals 0. Subtract 1 from each side. Subtract 5 from each side. Divide by 2 to get x equals -1/2, or the decimal. Divide by -2 here, so that gives me -5/2, or, -5 over -2, right? Divide by the -2. So that a negative divided by a negative is a positive, or if you try it on your calculator, you'll get 2.5. Yeah, so you'll see when there isn't a 1, there's definitely a bit more work here, isn't there? Okay, let's go ahead and find the vertex, and I'm running out of space here, so I'll have to write a little bit smaller, but I think we'll be okay. So vertex-wise, we know we need to find what's in between 2.5 and -0.5. So we'll just do 2.5 plus -0.5 divided by 2. That'll be 2 over 2, which is 1. Oh, that's nice. It's a nice number here, right? And so then we know that our vertex will be 1 comma something. We just need to substitute 1 into our equation. So it becomes -4 by 1 squared plus 8 by 1 plus 5. Okay. Negative 4 plus 8 is 4, and 4 plus 5 is 9. So we get 1 comma 9. All right, so how big of a graph do I need? Well, we have this negative, so we know the parabola is going down. We know the largest value, the maximum here, is going to be 9, so we need to get up to 9 on the y-axis. Our x-axis doesn't have to be super wide, and I don't see any negative y values, so I think we can kind of do the same graph as before, but just reverse it a bit. So something like this. And you're going to have to write kind of small on the y-axis, but not too bad. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the x-axis is pretty easy. 1, I'm just going to do bigger tick marks here. 3, 1, 2, 3. Okay. You don't have to have the same scale on both, as long as we get everything in. Okay, so let's go ahead and plot everything. Y-intercept is 0, 1, 2, 3, 4, 5. Not bad. We know that we have the point 1, 9, and that's our axis of symmetry. That actually allows us to get 1 point on the other side too, like so. You can see that my symmetry is not perfect here because of those gaps, but it's all right. I'll just maybe slide that point over just a bit. That's okay. And then we have our x-intercepts in purple. 2.5 is right here. 0.5 negative is right here. And I think we can go ahead and turn this into a downward facing parabola. Domain, all real numbers. And our range here, because this graph is going down, the highest it ever gets to is 9. So it can be equal to 9, and then it goes down below that, so less than or equal to 9. You could also do that by saying, we always put the smallest number first. You go from negative infinity, so you start down here, and the highest you get is equal to 9. All right, well, 2 trade-up cards to go. Let's take a look. James Bond. James Bond takes off from a platform. Remember, there's a few movies where he has like a jetpack and everything. Maybe that's what we're talking about here. His height h in feet, ironic because he's British, but that's okay. Not using meters this time, is measured in seconds t after takeoff using the equation h of t equals all that. At what time does 007 reach his maximum height, and what is the maximum height? All right, well, graphically, you don't actually need to make a graph here, but they have this negative here. We know the graph then is going to be a downward facing parabola. And if we're looking for the maximum height, we're really looking for the vertex. Unfortunately, to find the vertex of this, there's a bit of work to it, because we don't know what the vertex is from the equation. The only way we know how to find it so far, and we will learn a few other shortcuts in our last unit, but I think what we really need to find here are actually the x-intercepts first, because if we know the x-intercepts, we know the vertex is exactly in between. So let's start with the x-intercepts. Okay, x-intercept wise, we're going to set 0 equal to our equation, negative 2t squared plus 20t plus 48. Okay. Well, then from here, luckily, we should notice that we can actually divide everything by 2, or in fact, negative 2, because that will put a nice 1 in front of our t squared. So I'm dividing out the negative 2 from everything. That will leave me with t squared minus 10t minus 24. Okay. And then we can go straight to our factored form. We know it's t times t to get t squared. What multiplies to make 24 adds to make negative 10? Well, I'll go through it. It's not 1 and 24 because they're not 10 apart. It could be 2 and 12 though. 2 and 12 are 10 apart. I think it is actually going to be 2 and 12. And since we want to keep that middle term negative, then the 12, the bigger number, is going to match the sign of the middle term. And so we end up here. Negative 12 plus 2 is negative 10. 2 times negative 12, negative 24. Then we finish solving. T plus 2 equals 0, or t minus 12 equals 0. And it gives us 2 x-intercepts, negative 2, or t-intercepts in this case, and positive 12. So that's cool. We know this is like negative 2 and positive 12, just kind of keeping this for reference. But our ultimate goal is to find the vertex, so we should probably do that. Okay. Vertex-wise, we need to know what's in the middle of negative 2 and 12, so let's add those together. Divide by 2. 12 minus 2 is 10. 10 divided by 2, 5. So I know my vertex then is 5 comma something. What's the something? Well, we just need to substitute 5 into our equation. H of 5 equals negative 2 times 5 squared plus 20 times 5 plus 48. And then you can either do mental math, do it on your calculator, whatever's best for you. I see negative 2 times 25 plus 100 plus 48. Okay. This is negative 50, and I know 100 minus 50 is 50, so it's 50 plus 48, so I'm seeing 98 as a final answer. This means then that my vertex is 5, 98. So let's answer our question right now then. There are two questions here. At what time does 007 reach his maximum height? So the max height is reached at t equals, what was our input? Oh, t equals 5, right? T equals 5 seconds. Okay. What is his maximum height? Oh, well, the max height is 98 what? What were my units here? Right, I made fun of it. 98 feet. There we go. All right, last trade-up card. Let's see what we can do. The height h of a golf ball hit into the air by Tiger Woods at his most recent Masters competition. And that might age this video a bit, but he did actually just compete in a Masters competition in 2022. After t seconds is given by h of t equals negative 16t squared plus 64t. Create a graph of the situation, then use the graph to explain the maximum height of the ball Tiger hits, as well as when the ball hits the ground. So we have two things to do here. Okay, well, let's do the same as before. The first thing we'll want to find is the y-intercept. If we're going to make a graph, the y-intercept's an easy starting point. But you might be looking at this equation saying, I don't know if this is in standard form. Standard form is ax squared plus bx plus c, and there's no plus c at the end. Right? We've got our squared term, we've got our regular variable, but no c. But, of course, we should also realize you can always put a plus 0 if there's no c value. And so we'll find that our y-intercept, when we substitute 0 in, we actually end up getting 0 back out. Easy math there. Okay, next up, we'll need to find those x-intercepts. Okay. X-intercept-wise, we know we set 0 equal to this equation, negative 16t squared plus 64t. Now, this is something we covered a few times, especially back in 9.2. There are only two terms here. And when there's only two terms, really any time, but especially when there's only two terms, you should think to those shortcuts to try and put this in factored form. Okay? I notice there are two different t's here, so we do want to factor. But the nice part is factored form just means two or more sets of parentheses that each have a variable. And since they have a variable in common, they have a t in common, I'm just going to take the t out. That will leave me with negative 16t plus plain old 64. And I think that is actually factored form. Now, you could make your life a little bit easier too and actually divide both of these by 16, negative 16 even. So that would give you negative 16t times t minus 4. Right? If you multiply these, you get here. Oh, I'm sorry, you get here. If you multiply these, you get here. Or rather, back up to the initial. Now, you didn't have to take the 16 out. This equation is totally fine if you're comfortable there. I'll use this one, though, since I have it. So we're going to set negative 16t equal to 0, and we'll set t minus 4 equal to 0. Dividing by negative 16 gets us a time of 0, and adding 4 gets us a time of 4. So two x-intercepts or t-intercepts in this case. All right, let's go ahead and at least start making a graph here. Actually, that might not be a good idea because I don't know how high up the y-axis we're going to go. So let's find the vertex. Okay. Vertex-wise, I'll just use the space down at the bottom. I'm pretty confident I know what numbers between 0 and 4. Isn't that just 2? You could add together and divide by 2. But then we'll actually need to find the output here. So we need to do h of 2, which is negative 16 by 2 squared, plus 64 times 2. Okay? So we have negative 16 times 4, and then 64 times 2, I think is 128. So we have 128 minus 64, which takes us back to 64. All right, so it looks like our height here will end up being 64. And now we can go ahead and make that graph. Okay, so when we go through and make our graph, we know we're going way up the y-axis, right, all the way up to 64. And really, I'm just looking at some positive time values. So I'm actually going to go ahead and sketch this in like so. I'm just going to use the first quadrant here because I know that I have a t equals 0 and then t equals 1, 2, 3, 4 over here. That's all I need for the x-intercepts. And then the y-axis has to go up to 64. So let's just kind of maybe go by tens. That'll probably get us up there, right? So we have 10, 20, 30, 40, 50, 60, 70. There we go, 70 and 10. And so now we're just going to approximate a bit. We know the y-intercept is 0, 0. It actually shares the y-axis with the x-intercept. And then we have the point 2, 64. I should probably label this 2. 2, 64, let's see. We don't have to be perfect here, right? Here's 60, here's 70, 64 is somewhere in the middle. So here's my 2, 64. Okay? And then we can see our parabola. Now, let's get that axis of symmetry in there a bit. Oops. Second try. There we go. Now, we usually say we like 5 points to make an accurate parabola. This one only has 3. Now, you don't really need to be perfect here, but you could get 2 more points because this says go down 16 over 1. Right? So if we are at 64, 64 minus 16, right? You might have to do some mental math here. I'm looking at maybe 48. I think 48 and 16 is 64. Seems right. So that means we could go down to 48. So here's 10, 20, 30, 40. 48 is kind of right in here. And then over 1 in each direction. Over 1 in each direction. And those will give us 2 more points. You could, of course, have just sketched in your parabola. Something like that. There we go. All right. So we are supposed to use the graph to explain the maximum height of the ball that Tiger hits. Well, the max height is from the vertex, and it's going to equal 64. Did they give us any units here? No. It's just going to say 64, whatever units you want. Feet, meters, yards, something sounds good. Use it. And then we also need to explain when the ball hits the ground. Well, I think it's pretty apparent here that the ball hits the ground after 4 seconds. Hits ground. Easy enough. Okay, so we are hopefully feeling decently confident on how to graph. Again, this is really more of the same. You find the y-intercept, the x-intercept, the vertex, and you are good to go. The only new step for today is to find the x-intercepts. You had to convert to factored form. So hopefully today's lesson made a bunch of sense, and we are going to conclude this unit with 9.6, where we're just going to compare how to graph all 3 of our forms at the same time. And we can find some different shortcuts here and there. Thanks for tuning in, and I'm excited to have you back for 9.6.